today we have Stella Offner visiting us. She's assistant professor at the University of Massachusetts at Amherst. She's a graduate of UC Berkeley, is a Hubble Fellow at Yale, and is a postdoctoral fellow at Harvard's CFA, Center for Astrophysics. She is an expert on star formation, connected simulations, observations, which is the goal of theory in a sense. I'm very excited to hear what she has to say.
All right, thank you. All right, so today I'm going to be talking about movement towards a unified model for star formation, in particular motivated by 3 outstanding puzzles that have come up in the field. So you'll see where the forging order from randomness comes from. Right, so some of you might be thinking, well, we already have a unified model for star formation, and it looks like this, right? So we've had this picture for 30 years, right? So we have formation of cores that collapse and form protostars. At some point, these protostars launch a bipolar outflow, probably more like towards this stage than here, which is also as an outflow. Then there's a formation of accretion disks throughout this process, and at the end, there's the fried egg stage, at which point most of the gas has either been accreted or expelled, and you begin to get the formation of some planets. All right, but over the last decade, we've revised our picture of star formation to be one that's much more comprehensive, right, and spans a broad range of scales. So we've realized that star formation is connected across a broad range of scales by a number of important top-down processes. So if you think about molecular clouds, they inherit their metallicity, their turbulence from their global galactic environment. In turn, the dense cores that form within the clouds inherit their properties, mass, local magnetic field strengths from their natal cloud, and the properties of these dense cores, their angular momentum, again, turbulence and magnetic properties, in turn set the formation at the smallest scales and the formation of protostellar disks and the accretion process. So in this picture, as I've drawn it, all the arrows go in one direction. But of course, there are also arrows that go in the other direction. So bottom-up processes, or in other words, stellar feedback, which carry mass momentum from the smallest scales all the way up to the largest scales. So for example, we have protostellar outflows and winds acting on scales of a few tenths to a few parsecs. We have radiation pressure and ionization, which help to disperse some of the molecular cloud. And then finally, we have supernovae, which shuts off the star formation process locally and returns the gas back out into the ISM. So our new and improved picture of star formation is one in which star formation is a cycle of life. All right. So the downside of this picture is that all these scales are coupled together by very complex and nonlinear processes. Right? So to summarize, we start with some kind of turbulent molecular cloud, and then we have a whole bunch of nonlinear coupled processes acting on a broad range of scales. And then finally, at the very end, we have a star that comes out, right? So you could probably keep this up here for a few minutes, and people would be very entertained by it. But in any case, what I do in my research is take this complexity and replace it with this, right? So maybe less enticing, but nonetheless, doing numerical calculations can really help because we can turn processes on and off. We can explore the impact of different initial conditions and try and untangle what each of these processes is actually doing in the star formation process. All right, so the calculations I'm going to talk about today use the adaptive mesh refinement code Orion, which basically inserts smaller cells in regions of interest, such as around protostellar disks, and then follows the more boring regions, these voids, at much lower resolution. So it makes it computationally efficient. So in the calculations I'm going to talk about today, they use the Orion adaptive mesh refinement code. And the calculations will include and explore the importance of supersonic turbulence, gravity, radiation, magnetic fields, and the ideal limit, where the gas and field are assumed to be coupled. and star particles, which accrete and radiate, launch bipolar outflows, and winds. All right. So this talk is motivated by 3 recent observational puzzles, which I believe tie into 3 larger open questions in star formation. All right, so fundamental question number 1 is, how do magnetic fields shape star formation? All right, this is a big one. I'm not saying I'm going to answer this in this talk alone, but I hope to show how some of these recent observations can give hints for what's actually happening on scales where we can't resolve and explore magnetic fields. So another question, how does stellar multiplicity arise? Why is our sun a single star as opposed to in a binary or triple star system? And how does feedback shape molecular cloud evolution? So how does the energetics work across different scales? Is feedback really important, or is it not so important? All right, so my talk is structured around each of these topics. And I'm going to start with, how do magnetic fields shape star formation? So for each section, I have come up with a motivating quote to encapsulate the importance of the problem. So the quote that I picked for this one is from Mary Shelley. She says, "Invention, it must be humbly admitted, does not consist in creating out of void, but out of chaos." All right, so this quote evokes the idea of Frankenstein, right? So, maybe magnetic fields in the scenario, the Frankenstein of star formation. And in some ways, there are a number of parallels because they're quite bedeviling and complex and inescapable. All right. So let's look at fields in the big picture on largest scales. All right, so here's the torus molecular cloud. And this is actually a CO map that's been color-coded by velocity. So you have red shifted gas, blue shifted gas moving towards us, and green, which is some intermediate velocity gas. So there's no numbers here, but what you can see by eye is that the velocity structure of the clouds is very complex and turbulent. All right, so what are the magnetic fields doing? Well, recently, we've gotten these beautiful dust polarization data with Planck, which spans very large degree parts of the sky at relatively low resolution. But we can still connect that with what we see in this cloud. So we're fading into the Planck map. And in some sense, right, here is the dust polarization lines, which are tracing out the bulk field. In some sense, this looks much simpler, right? So it's almost as if this cloud is just along these strings of magnetic field that looks relatively orderly. All right. But of course, this is on large scales. And we like to know what happens at much smaller scales where we have velocity resolution from the CO and other tracers. How does that actually connect to what's going on with the formation of an individual star? All right, so let's go back to our 101 picture. All right, so people have done magnetized core collapse calculations of this stage of a forming protostar. And they get something that looks like this. Here, the white, the magnetic field lines. And so in this picture, the field might be orderly on large scales, and it gets wrapped up on small scales, right? And in this scenario, we have this disk, which is nicely aligned with the field. And we have an outflow coming out here, which is also aligned, or apparently aligned with the bulk field. All right. Now, we do have some data on scales like this with dust polarization. So here's one example from Stevens et al. 2013. So you can see it's very hard to do these dust polarization observations on small scales. You can see this is enhanced, that it looks like the field is fairly well behaved here and is nicely lining up with the outflow. All right. So how does that connect with larger scales? All right, so recently there was a nice survey by Chat Hole as part of his thesis, the Karma Tadpole survey, in which he tried to connect magnetic field measurements across a range of scales. So the smallest scales were done with Karma at a few arcsecond resolution. And then he had some larger scales from another survey. And he tried to connect these to figure out what was the relationship with the field and these forming protostars. All right. So you can see, right, so here's the small scale, here's the large scale. All right. In the left-hand side, things may be well behaved. But on the right-hand side, the apparent field direction is completely perpendicular from the outflow direction. All right. So that is a little bit confusing. Now, the nice thing about the survey is he finally had enough statistics to look at the distribution, right? So you can make a distribution function of the orientation difference between the outflow and the apparent field direction. All right, so he created a cumulative distribution function plot of this projected angle difference, right? And so if you expect them to be aligned, right, then you should get a distribution that looks like this. If they're pretty much aligned, the distribution should look like this. If they're not aligned and they're perpendicular, you should get this distribution. And if they're totally uncorrelated, you should get the random distribution. All right? And the survey says random to even perpendicular. Right? A very strange result. And this seems to hold not just for this larger scale, this core scale, but also even smaller scales, random to even misaligned, right? So a puzzling result. So this is puzzling result number 1, which is that outflow and field directions appear to be uncorrelated. And this is puzzling in part because we know that these outflows are launched in some sense by the magnetic field. So what is going on these kind of intermediate scales, on the core scales, we're getting this total misalignment?
Well, obviously you also care about the angle.
Yes, and that's going to play a part here. All right, so now how I can contribute to this problem. So I've been working on simulations of turbulent cores, which are magnetized with radiation following the formation and collapse of the dense core and the forming protostar. And so I have a set of calculations where we have different core sizes and magnetic field strengths. What I'll call an intermediate and a strong field, so mass to flux ratio of 2.5 and 1.5. So the simple conditions, the initial conditions are very simple. So the magnetic field is initially uniform, right? And there's some initial distribution of turbulence, right? So in the one picture, if the magnetic field is well behaved, you would get things that are nicely aligned, right? But if the magnetic field can get tangled in some way by the turbulence of their collapse, then you'll begin to get misaligned things. All right, so here's a movie starting with the initial conditions. This is log density. It's a slice through the middle. And these are showing you the orientation of the magnetic field. All right, so it collapses, forms a protostar in the middle, and then there's a launching of the outflow, which you can't see very well because you're looking at density, right? You're not looking at velocity. Right, so it'll happen again. At the very early times, you could see that there was an hourglass figure, which corresponds to the first 100,000 years after the protostar forms, and then the hourglass figure is lost as the gas is being expelled by the outflow. All right. So this is nice, but then the goal to understand the data is that we have to bring this into observational space so that we're comparing apples to apples. All right. So to do this, we need synthetic observations. So I'm going to define a synthetic observational as a quantitative model for the admission produced by a simulation and detected that the simulation is a real astronomical object at some point in the sky. And that means including things like noise, resolution effects, and instrumental effects. Right? So for this project, in comparing to CHAT's survey data, we co-supervised a student, Joyce Lee, who took the simulations and carried out this synthetic observation for a variety of different calculations. All right, so what she did is she took the simulation outputs, which give you distribution of densities and velocities, coupled these with a dust grain model. In this case, it's a fairly simple, standard icy grain model for molecular cloud. She then ran this through a dust polarization radiative transfer code, ARTIST, which I believe is publicly online. And at the end, she observed it as if these simulations were being observed by KARMA with a few arcsecond resolution, and as if they were positioned in the torus molecular cloud. All right. So she took the calculations at a number of different times and at 6 different viewing angles, and for each one, she made a synthetic polarization map. So here, these green lines here are representing the magnetic field direction locally, and this is the net mean field direction. And this orange arrow here represents the outflow orientation with respect to the field. All right. Now, one of the first and very obvious things that we notice in the simulations, we don't need a synthetic observation to look at, is that the outflow angle is not actually stationary with time, right? So the outflow might begin at one angle, and then over some time, it may change direction, right? And so starting, this 0 is measured from the starting position. Over time, and depending upon the viewing angle, the apparent direction of the outflow is actually moving by some tens of degrees over about 100,000 years, right, which is the class 0 lifetime. And the degree of that variation actually depends upon the magnetic field. So the stronger the field, the less the outflow is moving, the weaker the field, and the more turbulent the gas is, the more the outflow moves around. All right. So why is this happening? Well, it's because turbulent cores are, well, turbulent, right? So we know that observed cores have some velocity dispersion. So this is included in the calculations. And that means that accretion is not necessarily smooth, but actually varies in terms of its net angular momentum over time, right? And as the protostar is accreting gas in the small region around the protostar, the actual net angular momentum is changing. And a result is that this outflow orientation changes by as much as plus or minus 30 degrees.
Might I ask,
Yes.
What's the characteristic radius from which the outflow is emerging?
What is the characteristic radius?
Well, in other words, the launching radius.
In this case, it's probably maybe 40 AU, something like that. So it's around the accretion region of the protostar.
You're not generating that spontaneous.
That's right, yeah. So this outflow model is based upon the Matster and McKee model, and Chris isn't here to defend the model. But in any case, so it basically is sort of like an X-wind model, right? So they calibrated this using observations for what the opening angle and momentum distribution should be of protostellar outflows. Now, the reason that we do that is because if you do this self-consistently, you need resolution on the order of a stellar radii, right? Because the outflows are actually launched on the scale, if you believe these models, they're launched in very small scales from the inner disk and very close to the protostar. And the code can actually do that, but the problem is that then you would only be able to follow about a year in the lifetime of the launching, which means that you wouldn't be able to follow any time evolution.
Well, the reason, of course, I asked is just that the specific energy of 40 AU isn't that high, what eventually you get. So,
Yes.
So your feedback energetically is still fairly modest at this thing.
No. So this is what the subgrid model is determining. So it's based upon a protostellar evolution model. So that tells us
You're ramping it up.
exactly.
As though it was coming from the start.
Yes. So we're following the size, accretion history, luminosity of the protostar, and that determines the launching velocity of the outflow.
So they fix the momentum.
Yeah.
That's what this did.
Yeah. And so that's an important point, because this means that the outflow is largely resolution independent. So if you are doing it self-consistently, then your launching velocity would be entirely set by your resolution, right? So if you had 1 AU resolution versus half an AU resolution, you get a different launching velocity. All right. So Joyce took all of these different outputs, viewed at all of these different angles, and created a cumulative distribution function, following the one that Chat made from the observations. So here's the strong B field simulation, slightly more aligned. Here's the weaker one, completely random, and then here's the combined one. Right, so if we fade into Chat's data, we see that they agree a bit better with the weaker field case. All right, so that provides a better match. So it may mean that the observed cores actually don't have very strong magnetically dominated fields. Right. All right.
Distinction between high and low polarization.
Yes. So this is the. So he also subdivided the data into the percentage polarization. So I think the typical was only a few percent, but he subdivided the sample into low, which is maybe around 1 to 1.5%, and then 3%-ish were high polarization. All right. So
Physically, it's not clear what that means.
yeah, physically it's not clear what that means either. Yeah. So unfortunately, we can't build a unified model just from these simulations alone because we did not sample the parameter space very well. But it's beginning to point us towards something enticing that says one interpretation of the data is that the field strength is not influencing the angle and the order on small scales as much as we would think. So it points us towards a turbulently regulated picture of star formation. All right.
What did you assume about the grain alignment as a function of position? The efficiency data?
That's actually a plot in the paper, and we varied that to show that the results were depended on that a little bit, but not in terms of the large-scale distributions. I don't have that plot with me, but that's something we did actually look at. All right, so part 2. Well, I'm going to summarize before we move on to part 2. All right. So what we've learned is that outflows and magnetic fields are not aligned. And this is because turbulent accretion can create misalignment. Right. All right, part 2.
But
Yes.
You also said words, but not in text. That
Yes.
We're beginning to interpret that as the turbulence
Yes.
dominates.
Yes. Yes, it points towards a much more dynamic picture of protostar formation in which turbulence plays a role in setting the angular momentum of the accreting material. Right.
So if you look at this from the point of view of, I don't know whether it's any clouds with a uniform magnetic field, but all of the protostars wouldn't necessarily have outflows in the same direction.
That's right.
Is that related to this?
Yes. Yes.
Not in a single event way, but just the statistics of outflows.
Yes, that's true. So if they're not aligned on the small scales, then they can't also be aligned in the big scales. Given that we see all of this order, it'd be nice if that told us something about the magnetic fields on small scales, but doesn't necessarily tell us about the actual behavior of the protostar and the outflow accretion. Yeah. Any other questions before I move on to point 2? All right. All right. Second topic, how does stellar multiplicity arise? So not only do we want to answer this question, right? Why is our nearest neighboring star system a multiple star system? We like to be able to look at stars in the field, such as Alpha Centauri, and determine how a given multiple formed, right? And is there some kind of signature that tells us or points us towards the mechanism by which that multiple formed? So the quote to motivate this part of the talk is by Nietzsche. And he says, "You must have chaos within you to give birth to a dancing star." So I'll slightly modify this and say, give birth to 2 dancing stars. All right, so we're forming binary star systems. All right, so if we go back to our star formation 101 picture, this picture is actually very misleading, right? Because many, if not even most stars, actually don't form like this, but they actually form as part of multiple star systems. All right, so here's a very nice review plot from Dushin and Krauss, 2013, showing the multiplicity fraction and companion fraction as a function of stellar mass. All right, so the multiplicity fraction is just counting the number of binaries, triples, and quadruples over the total number of systems. And the companion fraction is the number of companions over the number of systems. Right? So they're both measuring the multiplicity. All right, so what this plot is telling us is that at low masses, stars are mostly single. But at high masses, they're mostly in multiple or binary star systems. All right. So you can also ask about the distribution of separations. And it looks like this with a peak of about 50 AU. Right? So this is a nice log normal. But as we know, log normals can hide lots of interesting physics. Right? So we'd like to look at this at the earliest possible time before dynamics and other processes have played a role in shaping and changing the distribution. All right, so looking back into protostars, there is a recent very nice survey by John Tobin of protostars in Perseus. And he did a complete census, I think down to about 10 AU or so resolution, and it came up with these values for the multiplicity fraction and companion fraction. So what he finds is that multiple systems are even more common for younger protostars. Right? So another survey that was done with Perseus was the masses survey with the SMA, led by Mike Dunham. And what they did is they took all of the wide binaries detected in Perseus, and they looked at the orientation of the outflows. Right? So they measured this relative angle between all pairs. Right? And what he found should look familiar. It is this random to even misaligned distribution. Right?
What mass cores are we talking about?
These are relatively low mass cores. So they're all under 10 solar masses. Probably the typical mass is more like 1 solar mass-ish.
So the stars are the solar mass or less?
Yes, these are low mass stars. Yep. So this is puzzling result number 2. Right? So these are pairs that are formed within the same core with separations of maybe a few thousand AU, and yet they don't seem to know about one another. Yet they seem to have outflows that are misaligned. All right. So puzzling result number 2, these wide separation pairs have misaligned outflows. All right. So I was very intrigued by this result. And it turned out that the simulations that I was doing to actually look at something completely different had this annoying habit of forming binaries. And this turned out to be very fortuitous because I could then take all of these wonderful binaries that had formed and actually turn it into a paper. All right, so my original study of looking at different core masses and magnetic field strengths had been to look at star formation efficiency in the dense gas. But that becomes much more difficult when you have 2 stars forming instead of 1. So it's not quite the controlled experiment I was hoping for. But in any case, I have enough of these simulations to do statistics, right? So with different masses and a variety of different turbulent realizations. So the turbulence is slightly different in all of the different cores. All right, so this is a volume rendering of a collapsing core where this scale bar is showing you the energy density. So it's basically rho v squared. All right, so this is nice because outflows will show up since they're very energetic. So they'll pop out very easily.
Actually, you said
Yes.
the real parameter, at least from the other ones.
It's 2,
It
yes.
is 2 of these as well.
Yes,
And what's
that's
the rho v squared versus v squared over 8pi?
Let's see.
Sure.
So let's see. So mass to flux ratios are 2.5, and the beta parameter I believe is like 0.02. I forget off the top of my head what that corresponded.
But the Mach number is like 7.
Yeah, it's maybe Mach 2-ish. It's slightly more than thermal. Yeah. All right, so the core collapses. Then there's the formation of the first protostar in the center, drives an outflow, and then a secondary forms right there. Right? So you can still see the outflow, though it gets progressively messier as the simulation evolves, because the outflow also drives a lot of turbulence within the local environment. All right. So we can take the sample of simulations and calculate the same multiplicity fraction that John Tobin did. So he got, for his class 0 sources, 0.57, and I get 0.58, which is actually too good to be true, I'm sure. But it does tell us something interesting, I think. All right, multiplicity is important at early stages, and it's maybe not as hard to make these multiples as you would think. Right? So what is actually happening in the calculations? Right? So what happens is the magnetic field introduces a preferred direction. The gas collapses along it, and you have this turbulent filamentary thing in the plane, which often fragments to form 2 objects. And the separations correspond to maybe 500 to a few thousand AU. And these evolve over time from wide to shorter separations of 50 to maybe 100 AU. Right? So an interesting result that Tobin published in this paper was the separation distribution. Right? And it's very clearly not a log normal. Right? So there are 2 peaks, right? Very clearly. And it seems like one of them is wide separation binaries, which seems very consistent with what we have here. And the second one could either be dynamical evolution or disk fragmentation, right? So clearly there's something very interesting going on at early times, right? So this makes one prediction, but what about actually trying to catch these systems in formation, right? It turns out there have been 2 Nature papers on this recently, where we have caught forming multiple star systems, right? So here's a system which is even pre-stellar. So there's one low-mass protostar. This is in B5. And at high resolution JVLA in ammonia, it broke up into 3 different condensations, which are each individually gravitationally bound and all bound together as a system. So the system might not remain a quadruple star system, but it seems to be forming very consistently with one of them at very early times. All right. But what about disk fragmentation? A year later, Tobin published this beautiful image, which is the first instance of what looks like a triple system forming from an unstable fragmenting disk. Right? So you actually have 3 objects here. All right. So these high-resolution observations turn out to be very difficult. I think ALMA is going to shed a huge amount of light on this particular issue. And so maybe in a few years, we'll finally get a statistical answer from observations rather than just one object of each case, which is what we have now. All right. But the point is to go back and try and understand the observed statistical samples. So to do this, I created a CO synthetic observation pipeline. So you start with the data from the simulations. You adopt a CO abundance model. In this case, basically just assuming that the cold gas has uniform CO abundance. We post-process this with a radiative transfer code, RADMC. And then finally observe it as if it's a real object, in this case with a few arcsecond resolution, as if it's in Perseus. Right, so here's Mike's data, right? The 2 distributions. And we can fade into the synthetic observations, right? So the distributions actually agree fairly well, right? If you're looking at the outflow contours, in both cases, they're pretty much a mess at this resolution. So there's clearly some voodoo involved in determining the outflow direction. But in either case, it's done by eye with the one caveat that if outflows are aligned, you can only pick out one outflow, so you have to throw that out. All right? And so it turns out that is the difference between a totally random distribution and a slightly anti-aligned distribution. All right. But the simulations actually do give us one thing that we can't observe at these early stages, which is the stellar spin of the protostar, right? And we can follow that as a function of time with our protostellar accretion model, right? So we can make these same distribution functions, and we get a random distribution, right? So this random distribution at this point should not be all that surprising, right? Everything just seems to be random. But again, this is maybe telling us something very interesting physically, right? So I've subdivided the simulations into a variety of different ways with different core masses and different times. And the takeaway message is that no matter how you splice it, the spins tend to be randomly misaligned, and they actually stay misaligned. And this result was actually surprising to me, because I assumed, well, they might start out being misaligned, but then as they move to closer separations, they would be accreting from the same reservoir gas, and their spins should begin to align again. But in the simulations, it at least turns out that they accrete enough gas further away when the angular momentum of the gas is uncorrelated that there's a relic misalignment that remains even at these close separations. All right? So this is a predictable signature that we could go out and look for among binary field stars. And it turns out somebody did. Now, there's not a large number of papers that have done this, and there's one that I know of, which is Hale 94. And they looked at spins in close and wide binary systems, where wide is a few hundred AU. And they found that the wide ones tend to be misaligned. All right? So this is actually a very encouraging data point. All right?
And the intermediate separations are still large number of pies are unimportant. So you need to be sure you're still probing the natal.
Yeah, so these are fairly natal in the sense that they're all less than, say, 0.3 million years. So they're basically over the main accretion phase.
Oh, I'm sorry, I meant
Yeah.
the Hale.
Oh yes, these are evolved stars. These are field stars, right? But the other thing that's missing is what is the role of magnetized disks and torques between the stellar spin and the disk, right? So that is something that's not included in the calculations, and there's been a lot of work on that dynamical issue. So that will certainly influence things. But this gives us one mechanism to start with an initial misalignment, right? All right, so in summary, these wide binary outflows are misaligned in observations. And this seems to be because the binaries, even within the same core, form independently. And as a result, the different turbulent accretion histories influences the evolution of their spins and outflows and results in this misalignment. Any other questions about part 2? All right. On to part 3. All right, so how does feedback shape? Yes?
Looking at the revolving ball diagrams there.
Mm-hmm.
So you've also got a misalignment relative to the
Yes.
line of sight or the plane of the sky.
That's right.
Can you tell anything about that from the axial ratios and outflow?
I don't think so. I mean, it's pretty difficult. You do have velocity information, so you might infer something, but it's difficult because you don't actually know the real velocity of the outflow, so you're just getting some component. I don't know, maybe Rachel knows something more about observing outflows along the line of sight, but my impression is that it's very difficult to infer too much. If you have the disk, then you have a much better handle on the orientation. All right, part 3. So the quote that motivates this part of the talk is from Sun Tzu. He says, amid the turmoil and tumult of battle, there may be seemingly disorder and yet no real disorder at all. All right, and so I will replace battle with molecular clouds. But the analogy of going to war on feedback, I think, is quite apt here. All right, so I first became interested in feedback in the form of winds when I started my postdoc at the CFA. Hector and Alyssa Goodman had just published this paper, which looked at a very extensive survey of Perseus in 12 and 13 CO, and they identified all of these large shells, right? This is actually position, velocity, and now this is velocity. You can see the outflow sticking out here. And then in position, we'll see the shells again, right? So there's these big holes in the CO. And so they took the data and they went ahead and they added up the total mass, momentum, and energy that they found associated with these shells. And the result was that it was a significant fraction of the total energy in the whole cloud, right? And much more than you get from bipolar protostellar outflows. So here's what you get when you add up outflows. Here's what you get for shells. So 50% of the cloud turbulent energy. All right. So their idea for this was that, all right, these are created by B-star winds. There are no massive stars in Perseus, so some kind of intermediate mass star. It might be a little bit older. Maybe it's a star that's wandered into the cloud with a wind, and these are actually creating these large shells. All right? So if you're not familiar with the distribution of mass loss rates for stars, there's a beautiful review article by Nathan Smith, which summarizes not only main sequence winds, but also winds from more evolved stars. All right. So here are the winds predicted from O and B-type stars. This is what we should have given the masses of stars that we see in Perseus. And this is what Hector and Alyssa inferred given the distribution of shell sizes and masses and momenta. All right. So this is puzzling result number 3. There seems to be an order of magnitude or more discrepancy between the observations of these shells and the model predictions. All right. So Alyssa convinced me to simulate this. All right. So I took turbulent molecular cloud, put in sources representing different mass stars, and followed the evolution of the wind into the local environment. All right. So this is actually a volume rendering in velocity, where the gray is a few to 10 kilometers per second, blue is tens of kilometers per second, and red is hundreds of kilometers per second, right? So these are very fast winds. All right, so as before, in order to compare apples to apples, I created synthetic observations, and Hector and Alyssa were looking at 12CO. So I created synthetic CO maps and went ahead and found, indeed, they seem to be correct. Right? You really need a huge amount of momentum and energy to generate shells of the size they observed. Right? So either there's a problem with the models, or there's maybe a problem with how we identify the shells. Right? So what they did is they went through the data and they visually identified them by eye, which is tedious and very difficult to reproduce. So somebody else might identify completely different shells. In fact, somebody did. So there's all these papers in literature where groups have written papers about the same cloud and come to completely different conclusions about the role of feedback there. All right. So I would like to focus on this problem. Right? How can we make the identification of feedback more rigorous? Right? And the answer I've come up with is machine learning. All right? So the idea is to develop an algorithm that allows us to automate the process so that it's both efficient and repeatable. Right? And the method that I've developed with help from an applied math student, Colin Van Oort, is based upon the convolutional neural network machine learning algorithm. Right? So the convolutional neural networks are formulated to work the same way our human brains work. Right? So they're good for identifying visual structures and features. Right? So this algorithm is a supervised learning approach, which means that you give it some input data set where you know the answer, and you let it train and learn its own set of rules. And once it's learned it and is able to understand the input data, then you can apply it to a new set of fresh data, and hopefully it will be very efficient at picking out the structure that you want. Right, so let me give an example of how this works. Suppose that you have an object. Let's call it a cat. All right. So if I ask you guys, why is this a cat? All right, you guys would say, oh, well, it has these characteristics. You know, it has an ear, it has eyes, nose, a tail, and a paw. Right? So, all right, good. But then somehow your brain is able to look at this image, which has an eye and a tail, and say, you know, that is not a cat. Whereas it's able to look at this image and say, ah, this is definitely a cat. Right? And it has some of the same features. All right? So, all right. So it turns out, if you think about it, this is actually a very hard problem, right? So this cat is white on white, and your eye is very good at picking that out. You don't even know how you do it, but it does it, right? It's very good at it. And why, right? So if you were an alien who landed on the planet and you just saw this, you would probably not say these objects were the same thing, right? So the reason you're able to identify it is because since you were a toddler, you've been looking at different examples of cats, and you formed your own mental training set for what it means to be a cat, right? Now, this is not exactly what your brain is doing, right? So your brain doesn't really see it in terms of eyes and ears and noses. What it sees is a set of patterns or filters, right? So in fact, this cat might be stored in your brain like this, right? So this is basically what this neural network algorithm does, right? So now I can explain what we're actually doing with the astronomical data, right? But still using cats, because I like cats. This is actually my cat, so in any case. All right, so we have some set of training data. And what we do is we identify the thing that we want in a pixel by pixel basis, which you can do in 2D or 3D, however you like. All right, so the algorithm takes this input data, picks a filter, right, convolves it with that filter, and gets a new image. We'll call it a feature map, which kind of enhances some of the aspects of the original image. Right? And then downsamples it to a factor of 2 lower resolution. All right? Then it applies an activation function, again, to bring out features, and then recompares it with the target data. All right? It then goes through this process m-1 times until it comes up with a set of filters, and then finally at the end it deconvolves back to the original image, right? So the reason for the downsampling is actually important, right? So you would like to be able to identify features on a broad range of scales in your data, whatever that data is. And so this allows you to find filters that are actually good for different scales, and you can change this parameter depending upon what scales you actually want the structure to be found on. So in this algorithm, it first does the training, so identifying filters in a set of models, does testing, it picks the best models, including, for example, how many different layers you want in the algorithm, and then finally it validates, so it checks against some new data set which you give it. Right? So simulations make an excellent training ground for this, right? So for example, in these wind calculations, we actually have a tracer field which traces where the wind is going in the calculation. So in every pixel, we know exactly how much of the gas is in the wind, right? So here's the input in density, here's the tracer field. And we apply our output to it, our machine learning algorithm to it, and it comes up with this. So a pixel by pixel finding of the structure, right? You'd say, well, by eye, this actually looks pretty good, but we need to quantify this. How good actually is this approach? All right, so we can come up with an accuracy metric which counts in a pixel by pixel basis, number of true positives, true negatives, and then takes the ratio of that between true positives, true negatives, plus false positives and false negatives, right? So if it identifies each pixel correctly as either belonging to a wind or not belonging to a wind, then it would be 1/1, an accuracy of 1, right? So for this particular example, it has an accuracy of 0.9, so it's pretty good. So you might also wonder what happens if you start with a simulation which has no feedback in it, right? So here's that image, and it actually does pretty well. This is the target, this is the output, and it actually does 0.96, right? So it's able to figure out when there isn't any wind as well, right? So we're in the process of applying this and tuning it for CO data. And so we hope to deploy this in the near future on these large Perseus CO data cubes, and hopefully for other regions where people have not yet really tried to quantify the feedback. All right. But in the meantime, the other data I'm interested in is dust data, right? So we also have lots of examples where we look at the Milky Way and we see these large shells, right? So I have a student who's taking the wind calculation using Hyperion to generate synthetic observation, right? And then observing it and then creating synthetic dust images like this. All right? Now this is actually a good approach because there turns out to be a really amazing training set for dusty shells like this. And it is called the Milky Way Citizen Science Project. So they took the Glimpse Galactic Plane Survey, and by eyes, people have gone to this website and actually identified all of these shells, right? So this provides an excellent way for us to use an existing training set and actually use the simulations to see if we can make it better, right? Or characterize it, characterize completeness, and see how well people do compared to our machine learning algorithm, right? So Duo has some preliminary results where he's making kind of cumulative distribution functions of the bubble number, right? And this bottom thing is the score, right? Which is one of the outputs for the likelihood of the object being a shell. So high confidence shells are here, and low confidence shells are over here. So you can retrain it using simulations, and it moves the entire distribution to the right, right? So the simulations are helping, at least in part. All right, so we can apply this trained algorithm to the glimpse data, to real bubbles, and then assess how well we improve or not the algorithm. So he's in the process of redoing the machine learning algorithm on these data sets. And hopefully by the end of the summer, we will have final results, which we will be able to write up. All right, so to conclude, right, what we've learned is that looking at these observations, mass loss rates are higher than predicted. As far as I can tell, the observers are correct, right? And one way to try and understand this problem is to really work on more automated ways of characterizing the structure and using this to quantify large samples of observational data, which we can hopefully compare with simulations as well. All right, so this brings me to my conclusions, and I'll just leave these points here and take questions.
Thank you. Any questions, Laura? I have a comment on the wind impact on clouds.
Yeah.
And I don't disagree with the observational result that something is producing bigger bubbles than would be produced by winds from PROTOSTARS.
Yep.
I'm pretty sure it's not winds. And the reason I say that is winds come off at several hundred kilometers a second, or from PROTOSTARs, they're more like 4,000.
Yep.
The beach starts at 1,000 or something.
Yeah, that's right.
They'll shock. They will produce a lot of X-ray emission. You never see that much X-ray emission.
Yeah, so I think 1,000 is probably on the outer scale. That's true. There's not a lot of X-ray emission, but people haven't really looked for it.
Oh,
You've looked for it? Maybe we can talk about that. But yeah. But at this point, what is being seen are these shells of entrained gas that are moving outwards.
There's something pushing on it.
Yes.
I'm just saying it's
Yeah.
not winds from stars.
Right. So I thought about this, and my idea is that it's a three-part contribution, with 1/3 being from protostellar outflows, maybe from early times, which are sweeping out some of the gas. Then second, there is some radiation pressure, maybe a small amount of ionization, which is getting rid of more of it. And then finally, you have the winds. The last, yeah. So I mean, it's a serious problem if you try and make the winds do all of it. But clearly, there's a large amount of momentum that's being injected in one form or another.
Yes, no, I totally agree with that.
Yeah.
This is an issue around B stars, lower mass stars?
All of the above. We see this in regions in Orion.
And around those.
Yeah.
But it's an issue in cases where you don't think the radiation pressure could be playing a role because
That's not so obvious. I mean, I wouldn't have thought so, but there's
Right.
something wrong.
Yeah, there's something wrong. Yeah.
I see. I mean, there could be buried O stars or something.
Not in this case, no. Yeah, Perseus is a pretty low mass region.
I'm
Yeah.
really confident in the case of O-stars that it's not winds.
Yeah.
Because the extra amounts would be like 5 orders of magnitude. That's not a small effect. Now, B stars, it'd be really interesting to go back and look at the kind of generated images of Perseus.
Not that I know of. Hector and I have gone back and forth with ways to maybe follow up and see what we can determine more information about the sources that are there. But
The
my
big
knowledge.
problem would be if you have slower shocks, like
Mhm.
V stars, and you just get, UV emission that gets reprocessed by the dust into IR emission, and you can't tell.
Right.
Whether it's
Yep.
just from the stars.
Mhm.
So it could be something like that.
Yeah,
But for the O stars, that doesn't work because they
Yeah.
are too fast.
right.
Any other questions?
Well, is there any clue from looking at different protostars, maybe the same mass and the same age, do they all have bubbles around?
So I think the answer is no, that all of the central objects look slightly older. They're not protostars. They're not embedded in cores there, which is why Hector and Alyssa had proposed that maybe some of the progenitors had wandered into the cloud and hadn't actually formed there, which would then take care of them being protostars with lots of surrounding gas.
I think they form.
Well, I was just wondering whether, depending on the environment in which the object was forming, whether it can take advantage of a relative void and just keep it a void. And so some would have them and some wouldn't, just depending on happenstance.
But as
Yeah.
Jack Welch said, stars form where the gas is.
Well, you would have to get gas into them somehow. It's not like you want
And
to keep what you would call a void around them.
Well, I can't tell any smaller bubbles because we didn't try to read, like look at the CO maps. And the bigger bubbles, the shells are always expanding.
yeah, that's right.
I don't know if that's true.
Yeah.
for little bubbles.
Yeah, and so these bubbles, you can use the dust or gas to estimate the mass in them. And if it had formed in a void, then there shouldn't be a lot of mass there, so there shouldn't be a lot of inferred momentum.
What's the mass times velocity you think you're talking about?
I don't know off the top of my head. They have a big table with it for all of the different shells.
So did you just say then the mass of what's collected in the shell is equal to the mass that would have been in the void?
Yeah,
Yes.
that's right.